Hello everyone. Today we are going to see about the topic neutron emission in fission process.
Introduction. Nuclear fission is a process in which the nucleus of the heavy atom is split into two or more smaller nuclei, along with release of large number of energy. During nuclear fission process, 2 to 3 neutrons are released. These released neutrons can then collide with the other nuclei, causing them to undergo fission reactions. This reaction creates more neutrons, leading to a self-sustaining process. In nuclear reactor, the control rods or other material can absorb the excess neutrons to slow down or stop the chain reactions. The given image represents the nuclear fission process. The fission reaction induced by slow neutrons in uranium-235-92 may be written as uranium-235-92 plus neutron 10 gives uranium-236-92, which gives the P1 plus P2 plus nu N10 plus Q. So the left side reaction is a slow reaction and the right side reaction represents a fast reaction where asterisk representing the uranium-235 is in highly excited state. So the P1 and P2 represents the fission fragments where nu represents the fast neutrons released per fission process. In the slow neutron fission of uranium-236, then the nu naught is equal to 2.47. Similarly, in the case of fission of plutonium-239, then the nu naught value becomes 3. Nu bar is the average number of fast neutrons released per fission. Since not all the thermal neutrons which are observed are capable of including nuclear fission, neta is smaller than nu. So neta is a asymmetric coefficient. The value of the neta can be written as neta is equal to nu sigma f divided by sigma a. So therefore, the absorption of the cross section shall be made up of two parts, sigma c and sigma f. Sigma c representing the radioactive capture cross section and sigma f representing the fission cross section. Absorption cross section is represented by sigma a, which is equal to sigma c plus sigma f. By substituting the above equation, we getting neta is equal to nu sigma f divided by sigma c plus sigma f. By dividing the equation by sigma f, we get nu 1 divided by sigma c divided by sigma f plus 1, which is equal to nu divided by alpha plus 1. Alpha representing the equation sigma c divided by sigma f, which is radioactive capture cross section is divided by the fission cross section. Then the applications of the neutron emission in fission process is nuclear power plants. In nuclear power plants, neutrons released during the fission sustain the chain reaction that produces the energy to generate electricity. In nuclear weapons, neutrons triggers the further fission reactions leading to a powerful explosion. Neutron activation analysis. In that, neutrons are used to analyze the materials by detecting the radiation emitted when the materials absorbs the neutrons. Advantages. Sustains chain reaction. Neutrons from the fission trigger forms more fission events, maintaining a continuous reaction. It releases large energy. Each neutron induced fission releases a huge amount of energy useful for the power generation, which generates useful isotopes. Neutron emission produces the radioactive isotopes used in the medicine industries, which improves the reactor efficiency. Neutron multiplication enhances the fuel utilization and reactor performance. Useful in research. Neutrons helps study materials through neutron scattering and imaging techniques. Disadvantages. Radiation hazard. Free neutrons are highly penetrating and pose serious health risks if not properly shielded. Chain reaction risk. Uncontrollable neutron emissions can lead to runaway reactions or nuclear accidents. Radioactive waste. Neutron activation produces long-lived radioactive byproducts requiring complex disposal. Material damage. The neutron can damage the reactor materials over time, causing embrittlement and reducing lifespans. Thank you.